After studying this module, you shall be able to analyze the structure of metal halide clusters, learn how to prepare a metal halide cluster, and study the reactions of a metal halide cluster. Cluster compounds of the early D-block elements and the lanthanides generally found to contain donor ligands such as halides, giving rise to metal halide, are clusters. The halide ligands can fill some of the low-lying orbitals of these electron-poor metals by sigma and pi electron donation. The metal clusters may involve MM bonds within a discrete molecular cluster or in extended solid-state compounds. Not all early D-block elements form metal-metal bonded compounds as discrete clusters. Many of them exist as extended metal-metal bonded compounds such as multiple chain scandium halides Sc7Cl10 and layered compounds such as zirconium chloride. Metal cluster halides of general formula M6X12 and M-4 M6X12X6, where M- is alkali metal, M is metal, and X is the halide, exhibit a number of structural variations because of the need to bond either terminally with a halide ion or sharing halide ions at all metal vertices. In these clusters, the 6 exo positions are always occupied by halide ions. These hexanuclear clusters are mainly formed by elements such as zirconium, niobium, tantalum, molybdenum, and tungsten. These metal clusters are readily soluble in water or polar organic solvents such as ethanol. Some of the metal clusters have been shown as follows. The halides in metal halide clusters often show very limited and lower dimensional interactions between the metals, and hence these exist as isolated cluster or small chains. Whenever stoichiometric number of halides per metal is less than the preferred coordination number, the coordination polyhedral is shared and it results in the formation of metal-metal bond, and hence metal halide clusters are formed. For example, the ZeI4 achieves coordination number of 6 by sharing two edges of the ZeI6 octahedron. Now, we shall have a look at the preparation of few metal halide clusters. Preparation of multiple chain or layered clusters. The metal halide clusters of early D-block elements such as scandium and zirconium are prepared in the absence of air and moisture because they adopt higher oxidation states of +3 and +4 when exposed to air and moisture. For example, zirconium chloride is prepared by reducing zirconium tetrachloride and zirconium metal in a sealed tantalum tube at high temperature. The given is the reaction where 3 times zirconium solid plus zirconium tetrachloride in the gaseous phase reacts to give 4 times zirconium chloride in the solid state. Zirconium chloride exists as layered compound where the zirconium atoms are within the bonding distance in 2 adjacent layers of metal atoms which are sandwiched between the chloride ion layer. Preparation of discrete clusters. Discrete metal halide cluster compounds are distinct from the extended MM bonded solids such as side chain or layered clusters and are often soluble. The ligands in these clusters may exist in various positions such as terminal positions and bridging 2 or more metal ions. Individual clusters may also be bridged by halide ions in the solid state. These are also synthesized under anaerobic conditions as described earlier, but in the presence of a reducing agent. For example, MoCl2 is prepared by the reaction of MoCl5 in a sealed glass tube containing a mixture of NaAlCl4 and AlCl3 together with aluminium metal as the reducing agent. This is given in the reaction where MoCl3 in the solid states react with aluminium in the presence of NaAlCl4 and AlCl3 to give MoCl2 solid plus AlCl3 liquid. On treatment with hydrochloric acid, MoCl2 forms the anionic cluster MO6Cl14 2-. Now we shall see the structure of few metal halide clusters. The solid compound of formula MoCl2 consists of octahedral MO clusters linked by chloride bridges. The structure of the anionic cluster MO6Cl14 2- consists of an octahedral array of molybdenum atoms with a chlorine atom bridging each triangular face and a terminal Cl atom on each molybdenum vertex. Interestingly, the terminal chloride ligands can be replaced by other halogens, alkoxides, and phosphines. As a result of high kinetic stability, these compounds can be handled in air and moisture, and the cluster can be either reduced or oxidized by one electron. The structure of MO6Cl14 2- is shown. In the rhenium trichloride cluster, the Re3Cl9 clusters are linked together, are linked by weak halide bridges, and provide starting material for the preparation of series of other Re3 clusters. These intercluster bridges can be broken by reaction with potential ligands in the solid state. For example, the reaction of the Re3Cl9 with chloride ion results in the formation of the discrete complex Re3Cl12 3-. Other neutral ligands such as trialkyl phosphines can also occupy these coordination sites and result in clusters with general formula Re3Cl9L3. The structure of Re3Cl9 is as follows. Now we shall study some of the reactions of metal halide clusters. Various metal halide clusters such as that of molybdenum, niobium, tantalum, and tungsten possess characteristic features such as high thermal stability, unique oxidation state of the metal ion, high melting point, and low vapor pressure. Considering these favorable features, metal halide complexes have been applied in catalysis reactions. Synthesis of quinolones. The metal halide cluster complexes such as Nb6Cl12, Cl2H2O4.4H2O, H3O twice, MO6Cl8, Cl6.6 water, and Ta6Cl12, Cl2H2O4.4 water have been utilized as catalysts for vapor phase synthesis of 1,2-dihydro-2,2,4 trimethyl quinolines from anilines and acetones. Synthesis of quinolines. In the reaction, we have aniline plus twice acetone giving compound 1 plus 2 water molecules. The catalysts in these act as solid Bronsted acid bearing a large counter anion by the reaction. Nb6Cl12 Cl H2O thrice OH gives H plus Nb6Cl12 Cl H2O thrice O whole to the power 1 negative. Isomerization of 1-hexene to 2-hexene. A variety of halide metal clusters of the general formula M6Cl12 Cl2H2O4.4H2O, where M is neodymium, tantalum, and H3O twice MO6Cl8 Cl6.6 water, where M is molybdenum, and tungsten, have been applied as catalysts for isomerization and slight hydrogenation of olefinic double bonds in the presence of stream of hydrogen gas at elevated temperatures. These metal halides possess octahedral structure and the three coordinatively unsaturated sites which act as active sites of the M6 cluster. Now we shall summarize what we have learnt in this module. Metal halide cluster compounds are generally formed by early D block elements such as zirconium, niobium, tantalum, molybdenum and tungsten, and lanthanoids with halide ions. These metal clusters are readily soluble in water or polar organic solvents such as ethanol. The halide ligands can fill some of the low-lying orbitals of these electron-poor metals by sigma and pi electron donation. The multiple chain or layered cluster metal halide clusters of early D block elements such as scandium and zirconium are prepared in the absence of air and moisture because they adopt higher oxidation states of +3 and +4 when exposed to air and moisture. Discrete metal halide cluster compounds are synthesized under anaerobic conditions as described earlier but in the presence of a reducing agent. For example, MoCl2 is prepared by the reaction of MoCl5 in a sealed glass tube containing a mixture of NaAlCl4 and AlCl3 together with aluminium metal as a reducing agent. The structure of the anionic cluster MO6Cl14-2- consists of an octahedral array of molybdenum atoms with Cl atom bridging each triangular face and a terminal Cl atom on each molybdenum vertex where the terminal chloride ligands can be replaced by other halogens, alkoxides and phosphenes. Because of various metal halide clusters such as that of molybdenum, niobium, tantalum and tungsten possess characteristic features such as high thermal stability, unique oxidation state of the metal ion, high melting point and low vapor pressure, the metal halide clusters have been applied in catalysis reactions.